Hello, and this time I'm talking about parametric equations and how to sketch the curves when you've got parametric equations. Now, I think this is a bit of a misnomer because having spent quite a while trying to do questions in this chapter and thinking, or this part of the chapter and thinking, blah, my neck, this is quite challenging. I'm going to say curve sketching is not the right title for this at all, because the way that the book is doing it and the way that it seems to want us to do it is to plot. And I was quite happy when it says draw the curve given by. I would absolutely read that to mean draw a table and work out the values and literally plot the coordinates and see what you get. If you get something that does that, great, wonderful. If you get whatever you get, you just have a look at it and go, oh yeah, look, nice graph. Absolutely fine. But when it says sketch, I feel like you should be able to look at something where it says sketch and think, okay, well, I understand what's going on. I understand the relationship, and I can sketch that. So if I said to sketch y equals 4x squared plus 3, then you would know, oh, well, it's kind of like a parabola, but it's going to be much tighter because it's got times by 4, so it's squashed in. No, it's not squashed in, it's stretched up, sorry. And then it's also 3 up, so it's going to look like that, okay? And that's what I would call sketching, and you could find out what that coordinate is. Well, we know what that coordinate is, it's just 0, 3. And if you have any other coordinates, if you had a parabola like this, you could find out those coordinates. Great, get all the interesting bits like that. But this does not seem to want us to do that. I don't think you can do that, or I certainly can't, with the parametrics. If I was going to sketch these properly, I would have to combine them into a Cartesian equation, which for this one isn't too bad, because you can just say that t equals x plus 2, and then substitute that in. You get y equals x plus 2 squared plus 1. So what's that? Oops, y equals x squared plus 4x plus 4 plus 1 is plus 5. So sketch that, easy peasy. It's going to go through at 5. It's a happy parabola. So it could come down here on this side, or it could come down here through that side. And looking at it, it doesn't factorize, so I'm just going to go and could do the quadratic formula, but may as well just plonk it into the calculator if your calculator does such things. 1x squared, 4x, and 5, and we get, okay, so we get imaginary root, and yeah, another imaginary root. So it doesn't go through the x-axis. There's no real number where it goes through the x-axis. So it's either going to come down like this and have a minimum on this side, or it's going to come down and be like this on this side and have a minimum on the right-hand side. So then we could carry on and we could find like a t. We could say how do we get that minimum value? Well, that minimum value of y we could work out actually using the parametrics. We could say the minimum value of y comes when this is a minimum. So when is t squared a minimum? When t is 0. That's 0. Then that coordinate for the y is going to be 1, whichever side it's on. And that's going to be when t equals 0. And so if we put that into here, when t equals 0, it's going to give us x is minus 2. So it is on the right side. Well, it's on the left side, but it's drawn correctly from where I did it last. That is at minus 2, and that's at 1. So, and we know that intersection point here is at 5. So we've got a sketch of the graph. But we haven't done it parametrically. We garbled it into this, and then we got the answers, and we just used the parametrics as a quick way of working out that minimum point. This is not what the book is expecting us to do. In fact, what it's doing in all of its examples is just drawing it out. Even on these ones where it says sketch, it's drawing a table, and it's getting values, and it's just doing that, and then plotting the values out, which I feel is a little bit of a cheat, but there we are. So anyway, let's look how we do that. So if we have got a graph with a load of, big line on it, big nice curve on it, each point on this curve has a t value. Yes, this strange middleman sort of variable t. And so this point here has a t value different to all the rest, and this t value can be transformed with this maths into a corresponding x coordinate and a corresponding y coordinate, which allows us to then draw the points. So what we need to do is we need to define a load of t values. So 0, well, hang on, t, x, and y. So we could do 0 all the way up to 2 pi. So we could do pi, over 2, 3 pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So that's nice, sort of going up in pi over 4s, and we can work out the values. Now you could do this manually, because you could, these are cos and sine, and so they should give exact values, so you could work them out with the roots and the root 3 over 2s and all this kind of stuff, but I'm not going to bother. I'm going to use my calculator, because why have a calculator and calculate things yourself? So I'm going to go on the table function, which is 9, and okay, it says a function of x, whereas I have x is a function of t, but it doesn't know I'm doing parametric, so just got to imagine that that is the t. So we're going to work out the x coordinates first as 3 cos of x and then plus 4. And it will do a second function, this calculator, which makes this so good for parametrics, because I can type the y in at the same time. So g of x should be g of t, but never mind, is 2 sine of x, should be t, but never mind. And we can then say, where'd you start? 0, please. Where'd you end? 2 shift pi. Now it's going to do it in decimal, but it doesn't matter, it's going to be accurate enough. And a step of pi over 4, please. Okay, and again, it doesn't decimal, but still, it's fine. And then we work this out. You can see that exact values like this, 7 and 4 and things like this, and 0 and 2, they're coming out. And then, all right, these are coming out as decimals, but let's face it, if you were actually plotting this on graph paper, well, you're not, where's root 2? You might know what root 2 is, but you still need to look for 1.4 on the graph. So it's still giving us sort of 3, 4 decimal places to plot on a graph, which for graph plotting is pretty darn accurate. And I think for these ones, certainly the textbook is expecting you to do the same thing. So although we actually sketched it a moment ago, in all the solution banks, it's just plotting them. So again, we'll just do the same thing. Start again. Menu 9. So this is just going to be x minus 2 equals, and this one is going to be x squared, no, wrong button, squared plus 1 equals, starting at minus 4, ending at 4, step of 1, and then we've got a load of values, and we're just going to plot them out. Okay, well, I'd like to see what they look like, so I think what we should do is go to everyone's favourite graphical calculator, Desmos. Okay, so here's Desmos, and the way you type these in for Desmos is like a coordinate. So you see I've got bracket, comma, bracket, just like a coordinate, and we put the formula for the x-coordinate, because really that's what these parametrics are saying. It's saying the x-coordinate is calculated in this function of t, and the y-coordinate is. And so telling Desmos that the coordinate of xy is this function of t and this function of t, and telling it the range of t's to use, all it does is exactly what I've just said to do, which is for each value of t, it works out, well, I don't know if it works out exactly like this, but I imagine it works it out, and then finds x and y values that correspond and plots them and makes it into the shape. So you can see this first one, the 3 cos t plus 4 and the 2 sine t, first question gives us a nice ellipse, which you would have seen from the table of values. If you'd plotted it on graph paper, then it would have made that quite nicely. Don't forget, of course, because you've got between 0 and 2 pi, and you're doing sine and cos, you do need your calculator to be in radians. If it's not in radians, then you're going to get some pretty weird numbers and get very confused. So make sure that you check that. If you do get weird numbers, you're like, this makes no sense, you've got to think, have I got it in the right unit? Okay, let's look at the second one. Well, we sketched this out ourselves, and actually, look, there it is, looking very nice. And we said that this minimum, point was at minus 2, 1, which indeed it is, and it goes through at 5. So we got that one pretty darn good. And then this last one we can draw there. Oh, and it's another little parabolic-like shape. I don't know that it is definitely a parabola, but it looks sort of nice little curve, just limited between minus pi over 4 and pi over 4, and we get this nice little curve. Again, I wouldn't have any... I think trying to get that without plotting it, without working out those values and actually plotting it, would be very difficult. You'd have to combine it into a y. You'd have to make it y as a function of x. Have to make a Cartesian equation and then sketch that. I'm not aware of being able to sketch directly from parametrics. I could be wrong, and if someone out there watching the video knows how you can take these and sketch them directly, then let me know. That would be amazing. But certainly the textbook that we're using just expects you in all of these, even when it says sketch, it just expects you to make a table, plot it out, and carry on like that, and just actually draw it rather than sketch it, which is slightly galling, but just because they've said the word sketch, and so I feel like we shouldn't be plotting, but that's what it's doing in the solution bank, so I think that's good enough for me. On that note, I think I shall leave it there. Do all the comments and things and all that stuff and jazz, but otherwise, cheerio.